All right, welcome everyone. It's a great pleasure to welcome Mike Kesden here to Arizona. Mike is an associate professor at the University of Texas at Dallas. He did a PhD at Caltech and then had a few postdoc positions at CETA in Toronto, back to Caltech for a little bit at NYU, and since then has been in Dallas, where he has continued to do really exciting research on black holes and relativity, for which he won a Sloan Foundation Research Fellowship, amongst many other accolades. He gives very enthusiastic, exciting talks, as Sam just pointed out. You know, maybe I'm being stupid to sit in the first row. He will keep you awake, I'm sure. So go ahead, take it away.
Thanks for that great introduction, Caitlin. And yes, I'd like to, it's nice that this is a small audience, so feel free to chime in with questions. This is kind of a work in progress, this talk, so feel free to chime in if I'm not being clear. So first of all, I wouldn't have been able to get this research done without my great collaborators. And so I want to give credit where credit is due. Nathan Steinley was a graduate student of mine. He got his PhD from UTD in 2021, and then he moved on to a postdoc at the University of Birmingham in the UK. Evangelos Stoikos is one of my current graduate students that's finishing up his research. Davide Gross is a longtime collaborator of mine. He started out as a master's student at the University of Milan, went to grad school in Cambridge, Einstein Fellow at Caltech, and now he's back. He's an associate professor in Milan. Daria Gongert is one of his graduate students, and Viola Durenzis is the second of his graduate students. And so for the paradigm that we're going to be talking about this afternoon is binary black hole formation and evolution. And so particularly in the isolated channel, where you start off with a pair of binary stars. We all know most stars are born in binaries. Each of those stars collapses into a black hole. So that produces a binary black hole system. And in a binary black hole system, each of the black holes generally will be spinning, and those spins can be misaligned with the orbital plane, just like we know the Earth's rotation axis is tilted at 23.5 degrees with respect to its orbital plane around the sun. And so the total angular momentum of this system will be the vector sum of the orbital angular momentum and the two spin angular momenta. And generally, if the spins are misaligned with the orbital angular momentum will be misaligned with the total angular momentum, and relativistic effects will cause this orbital angular momentum to precess and nutate. And that is going to lead to distinctive signatures modulating the gravitational waves that the binaries emit as they inspiral towards merger. So the work, I'm not going to be able to cover it all today, but the research that I'm presenting today is included in 4 papers that were published over the past 2 years. The first of these papers was part of Nate's thesis, where we looked up with, we made a simplified new model of how 2 binary stars collapse to form binary black holes, in particular with an eye towards how you could get configurations with large misaligned spins that would lead to that precession and nutation. So we made up a new model of BBH formation in this first paper. Then in the second paper, with our collaborators at Birmingham, this is essentially a pure relativity paper where we looked at the nature of precession in these binary black hole systems and defined 5 new parameters, which we'll get to, which give, I think, a very intuitive geometrical interpretation of what that spin precession is like. In the third paper, we then use these 5 new parameters that we had just invented to basically, given the constraints for the publicly available 90 events in the current catalog of the LIGO-Virgo-Cogra collaboration, we constrain those parameters and saw both what are the existing constraints with current events and what kind of future constraints could be possible at higher signal-to-noise ratios. And then finally, in the fourth paper in this series, we kind of combined this astrophysical model with these new parameters to basically predict how different scenarios of binary black hole formation could give rise to different kinds of precession nutation in the LIGO band. And so this is kind of an outline of where we're going this afternoon, and these papers are all published, they're on the archive, and more details are available if you're interested. Okay, so I'm going to skip a lot of I'm going to assume that this is a fairly knowledgeable crowd. I'm going to skip a lot of the ancient background about Einstein and general relativity, and just show you this picture, which I presume many of you have seen before, but this is, they call this masses in the stellar graveyard. This is a picture shown in blue are all the binary black holes and binary neutron stars that have been observed in the first 3 observing runs of the LIGO, Virgo, Cagra array of gravitational wave detectors. And then down here in yellow and red are the, just in X-ray binary systems, we had previously seen neutron stars and binary black holes. And clearly you can see the blue population and the yellow and red populations are very distinct. In addition to just the joy of discovering gravitational waves and winning the Nobel Prize, LIGO has already opened a lot of new, has a lot of surprises in store for us. There had been this hypothesized lower mass gap that, naively one might imagine there would be a continuum between the heaviest neutron star and the lightest black hole, essentially set by the neutron's nuclear equation of state. But in practice, people had seen kind of a gap, very little population between 2 and 5 solar masses, and yet LIGO has seen events in that gap. They call this the lower mass gap. Then there's also an upper mass gap. People had thought that above about 60 to 65 solar masses, stars would undergo these pair instability supernovae that would leave no remnants behind. And so you couldn't produce a black hole in that mass range, even though it would be certainly allowed by relativity. And yet nonetheless, LIGO has seen both progenitor black holes in that high mass gap and are producing black holes above that as well. And so LIGO has produced a lot of surprises for us. These are about the 90 mergers that we've seen that are listed in, it's the 3rd catalog of the first 3 runs. So there are about 90 events that we see here. Once LIGO gets up to design sensitivity in the next run or 2, we're going to be reproducing this sample almost every year. And then finally, in the future, in the next 15 years or so, there are plans. Initial LIGO that didn't see anything was the 1st generation. The current advanced LIGO detectors are the 2nd generation. There are plans for 3rd generation detectors, Einstein telescope, which will be underground in Europe to get away from some of the seismic noise, Cosmic Explorer in the US, which will have like 40-kilometer baselines instead of 4-kilometer baselines. And in terms of their both greater sensitivity and greater frequency range, these telescopes will yield about 100,000 binary black hole mergers a year and 1 million binary neutron star mergers a year. You'll essentially see binary black hole mergers out to the edge of the observable universe. And so I find it, personally really amazing. We've been doing optical astronomy for millennia, and yet, there could be a 20-year window between the first gravitational wave detection in 2015 and having the capability in 2035 to see mergers out to the edge of the observable universe. It almost reminds me of like the singularity with artificial intelligence. We've collapsed the age of gravitational wave astronomy into 20 years. Not that there won't be new mysteries beyond that. So seeing all these black holes, the next obviously question is, where did they come from?
So, wait, before you go
ahead.
Quick question.
Sure.
So I've seen like other versions of this, but I haven't seen Batman before. Is there something physical that I'm supposed to take, or did Eric just want to be Batman?
The masses are on the y-axis. On the x-axis, no.
Batman.
No. This is just clearly, I think they put the heaviest guy in the center, and maybe they've it looks like it's organized by final black hole mass, and they've just kind of moved outwards in each direction, giving you this,
What is the
Go ahead, please ask questions. What?
What is the arrow for?
Oh, it's just saying that, so 2 binary black holes merge to produce a binary black hole. So this is saying a black hole of 7 solar masses and a black hole of 13 solar masses have merged to produce a black hole of 19 solar masses. And because energy isn't conserved, the final mass is less than the sum of the initial masses. And in fact, it's of order 5 to 10% less. It's far more energetic than a supernova explosion. It's the most violent event in the universe. It's just that all that violence is coming out in gravitational waves, which couple very weakly to normal matter. Good questions. Yeah.
Real quick, what are the actual detections of the red points, the EM black holes? What does that refer to?
So these are EM is electromagnetic black holes. These are in X-ray binaries. So seeing like a main sequence star that's whose envelope is filling its Roche-lobe and is shedding mass onto a stellar mass black hole that's forming an X-ray accretion disk. I don't know off the top of my head which individual systems each of these red
Sure,
spots
sure.
corresponds to.
So the masses are then inferred from.
Yes, from the orbital motion of the, the masses are inferred. I mean, there's probably some degeneracy with inclination and things like, you see a Doppler shift, but you don't know is if it's edge on or, face on, there's some mass degeneracy, I think, yeah. Good questions, Andrew.
I was wondering, you mentioned the idea that there's this mass gap above 60 due to apparent stability supernova. I'm wondering if that could still be true and that, that stars exist not just in binaries, but higher order multiple systems. And so there could be like multiple mergers going on.
Yes, yeah. So yeah, exactly. So to make a black hole, I mean, mass, there's wins, mass is lost. Obviously, the black hole that you make is much less than the zero age man sequence mass of the stellar progenitor. If you believe, our understanding of these period instability supernovae, saying that essentially the maximum, native black hole you can make is whatever 60, and then we see something above that. One theory is right. Yeah, two smaller black holes, as we clearly see in this plot, that we can make smaller black holes that merge into, here an 80, 90 solar mass black hole. And then you have what is called a second generation merger. One of these guys then becomes the final guy here, becomes the initial guy here. I guess so that you're absolutely right. That is, if that's what you were saying, that's one of the theories of where these guys came from. One of the challenges to that theories, and I think, we were mentioning this in Sam's group, when binary black holes merge, obviously gravitational waves are emitted, they carry away energy, angular momentum, and linear momentum. And so you get these recoils that if the gravitational waves carry linear momentum in one direction, the final black hole recoils in the opposite direction. And those recoils can be thousands of kilometers per second. And so if you're making these things like in a galaxy or a globular cluster or something, a kick of 1,000 kilometers in a second is going to unbind you from anything. And then how would you pair up with another black hole? So that's a theory, but there's challenges to that theory. Good question. Other questions? Keep them up. I love good questions. So in terms of where do those black holes in that Batman come from, the bat signal of gravitational waves come from, there's more than two, but essentially the two most popular kind of channels, crudely, I call the cluster channel, and this is a picture of a globular cluster, and the isolated channel, this is a picture of probably an artist's imagination of what isolated binary stars would look like. And just very crudely, in the cluster channel, the black holes come first and the binaries comes later. So globular clusters are a very high density environment of stars. As we know, all stars are not born with the same mass. There's an initial mass function, a range of stellar masses. Black holes only form from the very heaviest stars. And even though they lose mass in their evolution, the typical black hole on that bat signal is way heavier than the typical subsolar mass of a star. And then through equipartition of energy, the heavier objects, you get what they call mass segregation. Essentially, the heavier objects in the cluster sink to the bottom of the cluster. And then through dynamical three-body processes, they violently pair off. And again, essentially, the heaviest guys pair up with each other. And that's a way of producing binary black holes. Individual black holes form in the cluster, and then they pair up after they sink down to the center. And one of the kind of hallmarks of this scenario, because of all of those dynamical processes in the globular cluster are, at wide separations that are highly non-relativistic, the spins are just kind of passengers along from the ride. And so essentially, since the black holes knew nothing about each other when they were born, you'd expect an isotropic distribution of black hole spins in binary black holes formed in this cluster channel. The other channel, the isolated channel, essentially the binary comes first and the black holes form later. This is kind of naively kind of the most obvious channel. If you start off with a binary of very heavy stars and each of those stars individually collapses to a black hole, that's another way of making a binary black hole. But in this case, where they were these two stars collapsed from the same gas cloud, and they interacted with each other as stars, they might have, memories, some residual memory of the orbital angular momentum direction of their host gas cloud. And you might expect a preference towards a line spin in this scenario. So if you could measure the spins of the binary black holes produced, and in particular the directions of those spins, you could identify which LIGO events came from this channel versus this channel. The reality is probably somewhere in the middle. Each of these channels is contributing, but we don't know how much for each one. Caitlin?
In the sort of current version of the isolated channel. What does isolated mean in terms of the initial separations where it's plausible that the supernova doesn't unbind the binary? Should they have never tidal interacted?
But that's a tremendous, we're gonna get, I think we're gonna get to that. That's an excellent question. Yeah, there's fundamentally the time it takes, in just at lowest post-Newtonian order, the time it takes for binary black holes to merge through gravitational wave emission scales as the fourth power of their separation. So if they're too widely separated that it takes much longer than the age of the universe to merge, they won't be, LIGO sources. And so yes, we do expect tidal interactions, and we're going to talk about that later in the talk. Very.
But I guess I'm saying then if they're tidally interacting, it's not the star formation that matters for their spins. It's the
right. They may or may not be tidally interacting, but you're absolutely right. Tidal synchronization and alignment, which we will be talking about, very much can affect both the magnitude and directions of their spins. You're absolutely correct. Good question. Other questions? Okay, so this is a busy slide. I'm not trying to make this too technical, but and also I don't know exactly the background of everyone in this audience. But what the punchline of this is trying to show is that, so here's the kind of the scenario that we're talking about. This is our detector. So LIGO and, all our gravitational wave detectors are L-shaped detectors. So we're imagining laser beams are bouncing back and forth along the 4-kilometer arms of our LIGO detectors. And when a gravitational wave passes through, it stretches and squeezes the space-time. You get incomplete destructive interference, and photons leak out into our dark port. And that's the signal that LIGO actually measures. And this is our binary black hole system. So here, this is our detector. We have the XY axes are the arms of our detector. Z would be directly above our detector. And so there's N is a kind of the position on the sky of our binary black holes. And then the binary black holes have an orbital plane, and they have an angular momentum L that's perpendicular to that orbital plane. These pictures are from this classic paper on the qualitative paper on the subject by Apostolatos and others. And so what is happening is essentially the gravitational wave detector, it's not really a telescope in the traditional sense, because gravitational waves couple so weakly to normal matter, you can't reflect them and focus them onto some CCD. It's really like an antenna. And so essentially we've got these two, and just like electromagnetic waves are polarized, except those are spin one field, so you have a linear polarization. Gravitational waves, since gravitational waves are a spin two field, you have a plus and cross polarization. And that's what this is showing intuitively. If you've got gravitational waves coming out of the board, they're transverse, just like electromagnetic waves. The plus polarization, if this is a ring of test masses, and T is the period of your gravitational waves, it will alternately stretch along one direction and then squeeze in that direction and stretch in the orthogonal direction, your ring of test masses. And so since this up and sideways thing looks like a plus sign, they call this the plus polarization, and then rotated 45 degrees with respect to that, stretching along this direction, alternatively stretching and squeezing along this direction. This looks like a cross, and so they call that a cross polarization. And so actually the signal that you see, this F plus and this F cross, this is your beam pattern response to these plus and cross polarizations that your detector sees. And then the plus and cross polarizations depend on the orientation of the orbital angular momentum of your binary with respect to the line of sight. And so this is the scalar product of the angle. Whoops, I keep, sorry about that. Skipping ahead a little bit. So if we see the system face on, that we see L and N are parallel to each other, then essentially this dot product is plus or minus 1 and it's maximized. And this thing in square brackets, they're out of phase 90 degrees. But if this is plus or minus 1, this will be 1 plus 1 is 2. 2 times, this will also be 2. So you'll get equal contributions from this. And so if it's face on, you'll get circular polarization, just like in E and M, circular polarization is equal, X and Y polarization, phase shifted. It's the same thing with gravitational waves. If it's just edge on, if this dot product vanishes, you'll only get plus polarization. Questions?
This is maybe a dumb question. When you said inverse arctangent, is that just tangent or is that?
Oh, sorry. This is just, I've cut this from their paper. It's double redundancy. This is, it's not, it's arctangent. It's not,
Okay.
Or inverse tangent. They double, that's pretty sloppy. Yeah. I didn't, not for my paper, but I agree that's confusing. Yeah. Good question. Maybe they'll revoke Kip Thorne's Nobel Prize because of that typo. Probably not.
I have enough issues with arctangent myself, that's why I was.
Yeah. So essentially we see, so the depending on the orientation between the orbital angular momentum and the line of sight, that will tell you how much plus and cross polarization that your detector gets. And then depending on where it is in the sky, that's how your detector is responding to each of those polarizations. This is our signal. And then we can decompose that signal into a time varying amplitude and a time varying phase. And so just propagating, doing a little trigonometry, this is what we get for the amplitude. This is what we get for the phase. Don't worry so much about the exact nature of these formulas. The point I wanted to make is that because we said the total, our binary system of each of these black holes is spinning, the total angular momentum will be a sum of the orbital angular momentum and the spins of each of the two holes. Here we see that they've chosen the z-axis to align along the direction of the total angular momentum, which is the vector sum of the orbital angular momentum. The two spins 1 and spins 2 sum to the total spin, and the orbit and the total spin sum to j. But as well, the direction of j is conserved on the precession timescale, as these spins change direction, the vector sum changes direction, L changes direction, and you modulate. You get modulations. Your orbital angular momentum is moving in a cone about the total angular momentum, and the opening angle of that cone is also varying. That's why this is kind of a messy, it's not just a nice, smooth, regular cone, it's kind of a messy nutating cone. And that leads to modulations that we can see as you inspiral through the band of LIGO. Questions about qualitatively what's going on here?
What is the x-axis of the second plot that you just
The
pointed?
x-axis of this plot?
Yeah.
Okay, good question. I apologize for that. So we have frequency on this axis in hertz. So LIGO, it actually, it's similar frequencies that obviously gravitational waves and acoustic waves are totally different. But LIGO is actually, by sheer coincidence, happens to be sensitive to frequencies comparable to what the frequencies that the human ear can hear. And so the way that this process works is these two black holes are orbiting each other. They're emitting gravitational waves. Gravitational waves are carrying energy and angular momentum away from the system, which is then taken away from the orbit, causing them to inspiral. And then just from Kepler's third law, as you shrink the separation, the orbital frequency goes up. And so this system, as you know, 10 hertz, that's essentially the lowest frequency that LIGO is sensitive to. Below 10 hertz, there's a background of seismic noise, you know, very low level earthquakes that are just you can't extract a signal from that background. And then ultimately at very high frequencies, you get shot noise. Higher and higher frequencies correspond to look shorter and shorter periods. And if there's a, you know, finite amount of photons in your, you know, beam path in that short period, only a very few photons hit the mirror of your detector, and then you get shot noise, Poisson noise from the discrete number of photons. And so that's kind of setting the range of frequencies that LIGO is sensitive to. And so what this is showing is, as you inspiral, if everything was nice and lined up, you'd have just a nice smooth increase in the amplitude of your gravitational waves as they inspiral. But because of this precession and this nutation, it's almost like a gravitational wave pulsar. Each time the angular momentum kind of precesses into the line of sight, you get a burst of gravitational waves. It's really kind of, then that's what each of these kind of bursts is showing you. Yeah?
We distinguish between two inclination that gives the same results for L.N.
That's a great question. If you had just one detector, the answer is no. LIGO itself has a detector in Washington State and a detector in Louisiana, but because they were conservative, were more worried about correlating signals between them, and so they're nearly lined up. But there's another detector in Virgo in Italy, and there's another detector, Kagra, in Japan, and so these are in different places of the Earth, and different, you know, the arms are oriented in different ways, and so essentially we can, with multiple detectors in your network, you can break degeneracies in the inclination like you're talking about. You're right, obviously there's not a unique choice of either Skype locations or angular momentums will give you the same scalar product. You're absolutely right. There's a lot of degeneracy in this formula. And that's actually why finding counterparts, people in astronomy departments are very excited and looking for electromagnetic counterparts for gravitational wave mergers. But because it's really like an antenna, when you're listening to the radio in your car, you don't really know where the broadcasting station is. We give them huge crescent-shaped, you know, 1,000 square degree patches to search in, and it's quite a challenge to find to look for a counterpart in that thing. Good question. Other questions? Andrew?
Is there a simple way to understand from this precession why the power is sort of double peaked with sort of a high and a low peak?
I think this is I think it's not entirely trivial. Sometimes this thing, if you think about this thing changing sign, you know, if it's really like near edge, this is a lot of modulation. This is, then, you know, it's almost like you're folding something over. The L dot N might can be positive or negative, but when you square it, you kind of, see what I'm saying?
Or, yeah.
What is held constant in that plot? Is
When-
it one system that is barreling in considering different?
I think I think you're really feeding me into the next slide. I think, yeah, that's a great question. What is so that's really the key. What is held constant? I think I'm going to try to postpone your question. I'm not going to dodge it. I'm going to postpone it. Okay, so what is held constant? So that's kind of that's feeding into this paper, that this taxonomy of spin perception mutation that we talked about. So there's a hierarchy of timescales. When you consider the inspiral portion of the merger, when essentially you can do a Taylor expansion in kind of the Schwarzschild radius divided by the binary separation, if that's a small number, or the orbital velocity compared to the speed of light is a small number, you can do a Taylor expansion of the gravitational waves in that small number. And then you can come up with a hierarchy of timescales. The shortest timescale is the orbital timescale that's given by just Kepler's third law. Then there's an intermediate timescale, that's the precession timescale, on which the directions of the spins and the angular momentum are changing. And that's if the PN1 post-Newtonian order is a small number, the precession timescale is longer by that small number to the -1 power. And then finally, the longest timescale is the radiation reaction timescale. That's the timescale in which the actual binary separation is shrinking in magnitude, and that goes that's up by 2.5 to the -2.5 of that small post-Newtonian orbit. And so when you have a hierarchy of timescales, what you can do is on the intermediate timescale, you can average over the short timescale, and you can hold constant the things that are evolving on those much longer timescales. And so on that intermediate precession timescale, the magnitudes of the orbital angular momentum and the magnitude of the total angular momentum are fixed, but the directions of the spin and the directions of the orbital angular momentum are not fixed. And you're averaging of the quasi-circular orbits, and essentially radiation reaction tends to circularize orbits. And so we're assuming if the binary is formed at a wide separation compared to these, the Schwarzschild radius, that you've lost any initial eccentricity that you had. And so we're averaging over quasi-circular motion on the orbital timescale, and we're holding constant the things in the radiation reaction timescale. And so this plot here is just showing you, I call this the source frame. So like Kip Thorne and his collaborator and Apostolados and those guys, if you choose the total angular momentum to have a fixed magnitude and direction in the z-axis, and L has a fixed magnitude, but not a fixed direction. And since the two spins are changing direction, their vector sum is changing both direction and magnitude. Well, you have essentially two different kind of phenomenon going on at the same time. You've got what I'm calling precession. That's L moving in a cone about J. So essentially by precession, I mean the azimuthal angle phi L projected onto the plane perpendicular to J, that's evolving, but the cone is open. And then as S changes magnitude, you still have this triangle, but like a drawbridge, theta L oscillates. And so as you go around on the cone, you're also, essentially this would be regular precession. And if you've got nutation, you've got oscillation like that. And so essentially this is kind of like a pie chart. This is what we're calling a taxonomy. We're kind of putting together all the different possibilities. So under the general rubric of precession, the first kind of decision you make is transitional versus simple. And by that I mean, does the direction of J remain fixed? And actually, there are two cases. In the transitional case, it turns out that L and S are nearly equal and opposite, so that their vector sum is small and that the magnitude of J is much less than L, then your binary kind of loses gyroscopic stability. Like when you're riding your bicycle, if you go too slowly, you don't have enough angular momentum in your wheels and you tip over. And so in that case, the direction of J can change and you get very exotic motion, very weird waveforms in that very special case, because in general, these two vectors are not going to be precisely equal and opposite. That's kind of a finely tuned case. There's also another case that I actually discovered with one of my earlier grad students, which I call a nutational resonance, where essentially, so you've got some precession period that it takes for phi L to vary by 2 pi. And then you've got your nutational period that it takes theta L to oscillate. And if those two periods are a rational multiple of each other, then essentially this thing will trace out a closed pattern. And then in that case, since the angular momentum is beams, you could average over that closed pattern. If it wasn't closed, it would average out to be just an axisymmetric annulus. But if it's closed, you can actually preferentially beam gravitational waves and tilt the direction of the angular momentum in the other way. And so essentially, first we say, is it transit? Both of these are kind of special cases because generally these ratios are not going to be rational multiples of each other. In the what they call simple precession, which is the more generic case, you can either have regular precession, which means no nutation, that theta L is fixed on the precession time scale, or the generic case that you get both precession and nutation going on at the same time. And this special case is also kind of a finely tuned case, but you get this either if there's only one spin. Obviously, if you only have one spin, the vector sum of a spin and 0 is always going to have the same magnitude, and so the magnitude of S is going to be fixed. If you have precisely equal masses, it's also going to be fixed. And also in this other case of resonances that I'm not going to go into in the interest of time, there's also a special case that all L and the two spins are coplanar and stay coplanar, and that's also a case of regular precession. Go ahead, Caitlin.
For the nutational resonances, is this something that you sweep through or in general, or?
You are very sharp. That's exactly true. So at any given binary separation, this ratio of these two frequencies is not going to be a rational number. But as you inspiral, these frequencies are changing on the radiation reaction time, and you will sweep through these resonances. Generic binaries, as they inspiral, will generally sweep through one or more of these resonances. That's absolutely correct. Other questions? Yeah, back there.
What is the typical ratio of S1 dot S2 and let's say L dot S?
In terms of unit vectors, or?
How strong is the coupling between the two spins relative to the coupling between the spins?
That's a great, if what you're, are you talking about couplings or misalignments? As we said, in the cluster channel, which is the spins are isotropic, and so the angles between both the L and the individual spins and both the spins themselves can be flat. Between cosine of that angle is flat between -1 and +1. Depending on the mass ratio of the binary, generally. At wide set, the orbital angular momentum gets bigger and bigger at your wider separations, where the spin angular momentum are just fixed by the mass of the black hole. At large separations, L is so much bigger than S that essentially this angle does get small. And you're again anticipating very wisely where we're going to shortly. So I'm going to defer further answering that question, but it is a very good question. Other questions? And so in terms of just this paradigm, this kind of taxonomy of spins, just very naturally, geometrically, we define 5 parameters. The precession, what I call the precession amplitude, that's just the mean opening angle of this cone. These brackets denote a precession average. There's the precession frequency, that's just how fast L is going around on this cone. There's the nutation amplitude. So essentially this plus and minus, essentially S is oscillating between a minimum value S minus and a maximum value S plus. And so as S gets bigger and smaller, this angle, just by the law of cosines, gets bigger and smaller. And so essentially that's the amplitude of the opening angle of this oscillation. Omega, the nutation frequency, that's just how fast you're oscillating. And finally, as you oscillate on the nutation things, and there's different projections of the spin along L, that will affect your precession frequency. And so this is another parameter that potentially matters. And so these are Ultimately, these are sourced by the spin, and you can calculate how misaligned spins give rise to these parameters. But these are really very intuitive geometrically, and these are the things. If you just plug these back into those formulas that we saw on the earlier slide, these are going to give very distinctive signatures that you can measure in both the amplitude and the phase of the gravitational wave emission. Questions? Okay. I'm loving this talk. I'm loving this audience. Okay, so this is just showing you, so those 5 parameters that I just defined in the previous slide, this is those parameters, the precession amplitude, nutation amplitude, nutation frequency, precession frequency, that variation. Don't worry about this. This is a technical point. And so this is showing how do those parameters depend on both the mass ratio of the holes. So Q is the mass of the smaller black hole divided by the mass of the bigger black hole. So 1 would be equal mass poles, 0 would be a tiny test particle falling into a black hole. And then that's what's on the x-axis. The color is showing you the spin magnitudes. Green are maximal spins, blue is 0.5, is kind of intermediate spins, and yellow is 0.1, that's kind of a smaller spin. And so what we see here is, as was anticipated in the audience, for equal mass black holes, essentially the orbital angular momentum will be bigger than the spins, and therefore the mean angle between the total angular momentum and the orbital angular momentum will be smallish. This is in radians. So if this is for maximum spins, this is like, and this is at a binary separation about 10 m. This is about 0.6 radians. So that's, well, less than pi, but less than pi over 2, but still 0.6 radians is like 40 degrees or something. That's certainly a non-trivial misalignment. And then as we get to small mass ratios, essentially the angular momentum will scale as the mass of the smaller particle. And so that can get then comparable to the spin of the larger hole. And once the angular momentum and the spin contribute equally, L and S contribute equally to the sum, then you can get misalignments of pi over 2. And then here for the nutation amplitude, again, it's not very, the peak of this is not very sensitive to the spin magnitude. We see it's like, so this is smaller numbers than this. So here, even for large spins, this is the 50th percentile. We're talking about 0.1 radians, which is 6 degrees. I mean, that's not, infinitely tiny, but at the same time, with our current signal to noise ratios, measuring these misalignments to 6 degrees is non-trivial. And this is just showing you again for an isotropic distribution that these things are not degenerate. They're certainly correlated with each other. I could talk a lot about the structure of what's going on here, but I don't, in the interest of time, I won't. But the point is that you could, they're not degenerate with each other, that in principle with enough SNR, and you'll see this in a few slides, you can measure all of these things. Questions?
Are these plots, what are these plots generated from? Is this like actual relativity simulations, or this is just, you're just sampling a bunch of different?
So this is, we're going to get, this is generated from, so we just assumed an isotropic distribution of spins. And then we have in post-Newtonian theory, we can calculate all these parameters, or, I left the equations out of this talk, but we can calculate all of those parameters. Ooh, we're getting ahead of ourselves. We can calculate all of these parameters in terms of the spin angle, magnitudes, orientations, mass ratios, et cetera.
I see. So these distributions are what you'd expect to see in a large sample of
right from that cluster channel. If things were isotropic, yes, this is what you'd expect from a large sample. Yeah, absolutely. Good question. Okay, so now we've introduced these things, we've defined them. This is just theoretically what you'd expect from an isotropic distribution. This is what we've actually reconstructed. This was a real event. This was gravitation in 19. This is an event in 2019, April 12th. There's actually even more processing events that have been released. This was one of the ones that was available at the time that we wrote this paper back in, it was only a year ago, but it's a rapidly changing, evolving field. And so here we're showing this is a traditional, what do they call these things? Corner plots, exactly. And so this is showing you, so this is 5 by 5. These are those 5 parameters that we talked about: precession amplitude, mean opening angle, nutation amplitude, precession frequency, nutation frequency, and the variation in the precession frequency. And the way that this is done is a little bit tricky. It's something that we call sequentially conditioned priors. So the blue plots are showing you the uninformative prior. So this is just a very broad priors on both the masses of the two holes and their spin magnitudes and orientations. The reason we have to do this sequential conditioning is because things like the chirp mass, if you've ever heard gravitational wave talks before, things like the masses, obviously you don't need precession just to measure the masses of the two black holes. And so essentially those masses indirectly affect, as we saw, the mass ratio definitely affects those 5 parameters. So if we want to get at precession and nutation, what we have to do is say, if we fix all the other non-precessing stuff, and then we look at kind of a uniform prior modulo all those other fixed things versus the actual posterior, are there differences between the two? And so what we've done here, the blue is the uninformed prior. The orange is the conditioned prior on the two masses. So it's basically saying, as we throw out all of our prior except those whose masses match the posterior. And you see that the orange distribution is very different from the blue distribution. And then finally, even if the spins are aligned with the orbital angular momentum, there won't be any precession or nutation, but that spin alignment will affect the orbital frequency and will affect the number of cycles per unit frequency during the inspiral. And so you also want to condition on the aligned components of the spin. And that's showing you that green cut, which has also made an effect. And then finally, if we compare to that the green fully conditioned priors to the red posteriors, you see for some of the parameters, the green and red contours are like right on top of each other. There's very little differences from them. The top of the corner plots are showing you just the 1D distributions of each of these parameters. And I guess the key takeaway of this slide is here. If you look at, this is the precession amplitude. It's kind of the easiest one to measure. Remember, we said the precession amplitude could be large by like an order of magnitude was larger than the nutation amplitude. Whereas this, the red and green are essentially indistinguishable from each other. If your prior and posterior are the same, you basically haven't learned anything from your data. Here, if you look at the red and green, they're really not the same. That the green is kind of continuous all the way down to 0, whereas the red, it still has a broadish peak, but it favors a non-zero precession amplitude. So there is an indication of precession in this event. And then you can reconstruct that, from our parameters that we've chosen. And so that was saying what we did with a real observed LIGO event on April 12th, 2019. This is showing you with a synthetic kind of golden binary. So we chose an event that had a mass ratio of about 0.4, and we've seen events like that, near maximal spins, and pretty large misalignments when they enter in bands. And we've, in addition to having a highly precessing system, we've also chosen pretty large signal to noise ratios. None of the events are quite this large. These is, signal to noise ratios of 45, 33, and 25 respectively at the 2 LIGO sites and at Virgo in Italy. And so we've never seen an event quite like this. But in the future, when we have our much more sensitive detectors, and we're seeing, 100,000 events a year, and this is not, in the future where we have warp drive and transporters, this is the future of 15 years from now, we will have a tail of events with these high SNRs. And this is showing you here, this is those Shane condition plots that we saw before. Here we see the posteriors are really nailing down with quite, significant detection, each of these 5 precessional parameters. But you still notice there is, this peak is a lot, tighter than this peak. And it is still harder to measure nutation than precession. That's just the nature of the beast in terms of imprinting the signal.
Mike?
Yeah.
Are you fixing the sky location as well?
Yes, for this event. I don't know. I don't remember off the top of my head exactly which parameters, but this particular event has some fixed sky location.
And for the previous binary, the GW19 that you had, did the same thing?
No, that is what we've basically just done for this event. So LIGO made, I'm not a part of the official LIGO collaboration, but they haven't made all their data public, but all the data, near the events that they published have been made public. We've just taken, they publish it into, there's different waveform families. It's complicated, but for the families that have individual spin components, we've just taken the posteriors on all the different posteriors in their MCMC plots and just calculated in terms of those parameters our 5 new precession parameters. And so we think these are more illuminated. In principle, kind of the X component of the spin of black hole 1 and the Y component of the spin of black hole 2 give rise to these things. But those things are all changing in the precession timescale, and the degeneracies in that weird kind of Cartesian space are kind of, this is a much more kind of, at least we think, intuitive way of kind of understanding the imprint of the signal. But these are not assuming, this is just, we're taking the posteriors that they give us, which have some crazy banana plot of sky locations. This, whoops, we're getting ahead of ourselves. Sorry, I don't remember in detail. I suspect they didn't fix the sky location. This was kind of just a one subsection of this paper. Most of the paper was on analyzing the actual events, and this was just a late add-on of the synthetic event. But I bet with these crazy SNRs, you probably have a really good sky location compared to real events. Good question. Other questions? If they are returned. And so I think we are making poor time, but that's okay. I'd rather give a fun talk on 3/4 of my talk than get through the whole material. So remember, there were essentially those 4 papers that I told you at the beginning. 2 of them were kind of relativity papers, and we've kind of done that half of the talk. The other half was like, models of binary black hole formation that I was claiming was going to, those are what all initialize the binaries and would give us in the isolated channel what are the values of those parameters. And so this is a very simplified model. I'm going to, like when you're baking a cake of binary black hole cake. First, you list the ingredients in the cake, and then you give the recipe of how you combine those ingredients to make a binary black hole. These are 3 of the ingredients. So this is a kind of Cliff Notes version of what's going into the recipe. We've got Roche-lobe overflow. So we know, assuming this is an audience mostly of astronomy people, stars evolve and their radii increase as they evolve. And since the binaries have to be pretty tight if they're ever going to form binary black holes that merge in the age of the universe, when a star evolves such that it fills what's called its Roche-lobe, it's essentially the set of orbits gravitationally bound to one member of the binary. Essentially, you get Roche-lobe overflow. The envelope of the star will slip out, through this Lagrange point and potentially go to the companion. The second ingredient is when Roche-lobe overflow occurs, there's essentially 2 possibilities. One of them is stable mass transfer. If your companion is capable of accepting and accreting what is being donated to it through that Lagrange point, then it will accrete some fraction of the mass, in an accretion disk. And this accretion can increase both the mass and the spin of the companion. And depending on where we are in our binary evolution scenario, that companion, if it's still a star, it might be either a main sequence star, it might itself have already lost its envelope and then be just kind of a naked Wolf-Rayet star, or it may already have collapsed to a black hole itself. And in each of these cases, it's going to affect the outcome of the binary black holes that are produced. The other possibility, instead of stable mass transfer, is if your companion is not capable of accepting the donated mass, then what you do, I don't know if you can see it, there's this kind of peanut-shaped kind of halo around both members of the binary. This is called a common envelope. And you get kind of what they call common envelope evolution, where essentially the envelope of the evolved star forms a common envelope about both members of the binary, and then orbital energy and angular momentum from the binary are transferred to that envelope, which unbind the envelope, but it comes at the expense of shrinking the orbit by potentially almost a factor of 1,000 potentially. And this is actually critical if we want to get the stars close enough together such they can merge through gravitational radiation in a reasonable amount of time. Having at least one episode of common envelope evolution is critical. Finally, I'm going to call this loosely a supernova. By that, I mean not necessarily the luminous supernova that astronomers love to look for, but just the idea that ultimately, if you're going to make a black hole, the core of the star has to collapse into a black hole. And when that collapse occurs, Generally, it's not going to be perfectly spherically symmetric, and not 100% of the core will go into the black hole, but there can be ejecta. That ejecta can carry away mass, angular momentum, and linear momentum. And so if the ejecta has some net linear momentum, this is not a gravitational recoil. This is just a good old-fashioned explosive recoil. If the supernova ejecta is preferentially carried away in one direction, the binary will kind of recoil in the other direction. The remnant will recoil in the other direction. And if that direction of the recoil is misaligned with the original orbital angular momentum, the new angular momentum post-kick will tilt the angular momentum of the binary. And if the spins of the companion remain fixed and you tilt the angular momentum of the binary, that will lead to the misalignment, which is kind of the critical ingredient for us to get precession nutation. And this is kind of a conservative assumption that we're assuming that all of the tilts just come from these recoils and there was no natal kind of tilt. Questions? Okay, so those were the ingredients. How do we actually combine those ingredients to make binary black holes? Kind of and Nate was the one that, my grad student, Nate Steinweg, was the one that kind of recognized you could break down all the, it's quite a complicated, binary stellar evolution is certainly a highly non-trivial process, but you could kind of classify it into what he called scenario A and scenario B. And within each scenario, he then decomposed it into pathway 1 and pathway 2. So we've got pathway A1, A2, B1, B2. And what do these mean? So in each of these cases, we start off with some main sequence stars. They're losing some mass through winds. They're evolving. The primary, which is what we're calling the heavier star, fills its Roche-lobe. And then you essentially have two possibilities: either it's stable mass transfer and you accrete it onto the companion, or it's unstable mass transfer, common envelope evolution. So if the first episode of mass transfer is stable, you need at least one common envelope evolution. So if the first one is stable, the second one's going to be unstable. If the first one is unstable, the second one can be stable. The rates are dominated by one, but only one episode of common envelope evolution. So that's what distinguishes stable then unstable is scenario A, unstable then stable is scenario B. And then the difference between pathway A1 and A2 in each scenario is, if you notice, if you look at these events, here the supernova of the primary is before the Roche-lobe filling of the secondary. And here it's reversed. The secondary fills its Roche-lobe before the core of the primary collapses. This is really governed by mass ratio. If you have equal mass things, just by perfect symmetry, they both fill their Roche-lobes at the exact same time. They both, it'd be like perfectly symmetric. Obviously, that's finely tuned. The typical lifetime of this Wolf-Rayet star, you basically lose your envelope, you become a Wolf-Rayet star, and then the Wolf-Rayet star collapses into a black hole. The typical Wolf-Rayet lifetime is around 300,000 years, which is certainly not a lot of time compared to stellar lifetimes. If the mass ratio is nearly equal, such that their main sequence lifetime difference is less than 300,000 years. And remember, these are very massive stars that have very short lifetimes. It's not like the sun with a 10 billion year lifetime where 300,000 years is, really a short amount of time. Then you can essentially, if they have a nearly equal mass ratio, the secondary can fill its Roche-lobe while the primary is still a Wolf-Rayet star and has not yet collapsed to a black hole. And so these are essentially, that's kind of it depends on masses, mass ratios, binary separations. It's quite all of these, we can categorize as a function of the parameters in our model, which of these four pathways we're on. Questions about this? So within this story, there's essentially three different ways that our black holes can acquire spins. And obviously, if there's no spins, there's no precession or nutation. Kind of the first, most obvious way you can acquire spin is if you're born with it. So here, if we've got stars, and we know stars rotate, stars have non-zero angular momentum. If your star has some angular momentum, and when it collapses, people don't know how efficiently there's kind of core envelope coupling. And so as you kind of collapse, if angular momentum is conserved, you start rotating faster. And if you have differential rotation, you can transfer angular momentum outward. People don't know for sure how efficiently angular momentum is transferred, how tightly the core and the envelope are coupled to each other. But if they're not perfectly tightly coupled, your Wolf-Rayet star can retain some angular momentum, and then when it collapses to a black hole, that black hole will be spinning. And remember, because black holes are so compact, you don't need, in terms of stellar scale, because stars are so much more extended than black holes, all that much angular momentum to have a highly spinning black hole. The other way that Caitlin had anticipated were tides, that again, because this common envelope evolution brings these stars very close together, they can be close enough that they can raise tides on each other. And again, this really keys into when we're in pathway 1 or pathway 2, because if your object has already collapsed into a black holes are really compact. You can't raise tides on a black hole. You can't kind of tidally synchronize a black hole. But if you're a Wolf-Rayet star, black hole can very much, or anything can raise tides on a Wolf-Rayet star. And so you can both spin up the star, you can synchronize the stellar rotation with the orbital frequency, and you'll also simultaneously align the spin of the star with the orbital angular momentum. Question?
How do tides cause spin?
Generally, so you raise like tidal bulges, like the near side of the star, so you raise tidal bulges. If there was like generally there's dissipation in these things. It's there's damping, and so that tidal bulge is not perfectly aligned with the line of separation between the two objects. If the thing is, depending on whether it's rotating faster or slower than the orbital frequency, the tidal bulge will either lead or lag the line of separation. And so then angular momentum will be either transferred back or forth from the orbits of the rotation and vice versa. If you look at the moon, we always see the same face of the moon, right?
Yeah.
And that's because the moon is tidally synchronized with the Earth. It rotates around the Earth every 28 days, but it also rotates around its axis every 28 days. So we always see the same face.
Yeah.
And that's not, so yeah.
It's not a coincidence.
Not a coincidence.
Okay.
Yeah.
Yeah, one question for your comment on, you don't need a very big initial angular momentum to generate of a star to generate a big initial angular momentum for a black hole. In other words, for let's say a classical object, if you naively calculate L over m squared, it will be way bigger than 1.
Right, exactly. Like the Earth is rotating on its axis once a day. If you just you said G equals C equals 1, what is chi Earth? It's like 10 to the 6 or something, it's humongous. That's what I meant exactly.
For the sun as well.
For the sun as well, yeah. So tides, that's another way you can produce spinning black holes. And finally, accretion, as we said, if the mass transfer is stable, mass transferred from the envelope of the primary, where the second will fill from the donor, will get accreted by the recipient, that will increase both its mass and its spin. And also, so that's how you acquire spin magnitude, and you get spin alignments again through these kicks. And as Caitlin was saying, if the kicks are too large, they'll unbind your binary, and so you won't get a binary black hole. If they're too small, you won't get appreciable precession nutation. You want the kick and the orbital velocities to be comparable, kick slightly smaller to get decent sized tilts. And so it's again a Goldilocks scenario. We need the right natal tilts to give us detectable precession and nutation. And so I don't know, time wise, I've got like 3 minutes. See you. I don't know. I'll beg your indulgence. I'll maybe just go through this quickly. Now I was just wanted to bring everything together, combine those parameters, those precession nutation parameters I was talking about at the beginning of the talk with these different pathways of binary black hole formation that I was talking about at the end of the talk. Here we're seeing, this is chi effective. This is actually the line component of the spins that doesn't lead to precession. This is again our precession amplitude. This is our nutation amplitude. This is the nutation frequency. Don't worry so much about that. And so these are these two, the pathway A1 and pathway A2. Just to remind you, in blue, we have stable mass transfer. Then the primary has a core collapse. And then the secondary fills its Roche envelope with common envelope evolution. In A2 with comparable mass ratios, the secondary fills its Roche-lobe before the primary collapses. And we see that looking at these plots, this is showing you, in this scenario, FB is telling you for that Wolf-Rayet star, if it was spinning at breakup, essentially it'd be spinning so fast that material would be, the centrifugal repulsion would overpower the gravitational attraction. your thing wouldn't hold together. So if I just parameterizes the spin of the rotating Wolf-Rayet star as a fraction of its breakup value. So 0 is non-spinning, 0.1 is it's spinning at 10% of its breakup value. And we see that, well, first of all, differences between these plots. If you're actually claiming I could measure these parameters and tell apart these pathways, you see a little bit here that even at non-zero, at 0 natal spin, you still have some aligned spin in pathway A1. And that's because if you have a kick before from the supernova 1, before the common envelope evolution, you'll have some 5% tail that if the kick velocity and the orbital velocity are nearly anti-aligned, you'll end up with a very small pericenter and you'll get tidal forces that can spin you up even in this scenario. Looking at the precession amplitude, this was just tuned to show you, these plots look very similar. This is showing you the 95th, 5th, and 50% contours of each of these parameters. These are very hard to distinguish, but you notice these are very much distinguishable, that the precession amplitudes are the same in pathway A1 and pathway A2. But the nutation is much larger in pathway A1 and then pathway A2. And why is that? That's because in pathway A2, remember that was the one where they had nearly equal mass ratio, such that the secondary filled its Roche-lobe before the primary collapsed to a black hole. And remember we saw in that early, when we went to that taxonomy chart early in the plot, when you have perfectly equal masses, the nutation frequency goes to infinity. Essentially, they become locked. And so you have no nutation in that case. And so essentially in this pathway, you're going to have very sparse nutation. I don't know how much, we can just skip to the conclusions, or you can indulge me with another 5 or 10 minutes. Does anybody have any preferences?
I think, maybe if you want to
Let me skip.
take 1 more minute or 2.
Okay, let me take 1 more minute. So anyway, so in those scenarios, I'm nearly done. So we just talked about the inheritance scenario. In the tides scenario, where essentially tides were the source of the spins of the 2 black holes, then you could get, fundamentally looking at the 2 different pathways, now they look very different. In pathway A1, in this case, you had very small kicks to avoid unbinding the binary before common envelope evolution. And with these small kicks, you get small misalignments. And so essentially there's no precession or nutation in pathway A1. In A2, you could get, essentially with larger, you could have larger kicks post common envelope evolution and survive being unbound. But if tides are giving you the spin, they're both spinning you up, which is a good thing, but they're also aligning you, which is a bad thing. And these amplitudes compared to the other spots, these are very small, hard to detect amplitudes, particularly for the nutation. It's very hard to get nutation just due to tidal spins. And then finally, the accretion, that was the third source of spins. This would be in that pathway B, that scenario B, where the second event was stable mass transfer. And what we see here, if you want to differentiate B1 versus B2, and these look very different. The big difference here is that in pathway B2, where, this is a typo, these should be switched. I just was cutting and pasting and I didn't switch them. Here you're accreting onto a Wolf-Rayet star, whereas in the green scenario, you're accreting onto a black hole. Obviously, the radius of a star, it's like a solar radius. It's way larger than the gravitational radius of a black hole. Essentially, you've got a larger moment of inertia. A star has a larger moment of inertia than a black hole of the same mass. And so you've got a bigger lever arm. The same amount of accretion with a bigger lever arm can torque you up and supply more angular momentum. And so I'm done. I'll just put up my conclusions and spare you. I think given all the questions, I think the timing worked out pretty well. But the punchline is that we already see, we're going to see 100 black holes a year with our current detectors. We're going to get 10 to 1,000 times more when the 3G detectors come online in 15 years. Some tail of those events will have great SNRs, which will allow us to measure precession in our binaries, and that will tell us key elements of the evolution of where those systems came from. So I hope you enjoyed the talk, and thanks for your attention. I'll take even more questions.
Hey, you can call your
Sam?
Yeah, what's the top line scientific motivation for measuring precession?
The top line scientific
Is
motivation.
it the goal or is there the means to some other information?
Well, LIGO, all these, one of the things that's so exciting about LIGO is it's both, you know, a physics experiment and an astronomical observatory. I mean, I've token mostly on the astronomy side in this talk. If you accept that GR is, you know.
Well, maybe I missed it. What's the astronomical, like what specific thing does, we see precession, you know?
Well, I guess going back to near the beginning of we want to know, we see binary black holes. We want to know where they came from. There were those two, there was that cluster channel and that isolated channel. The cluster channel predicts isotropic spins. The isolated channel predicts at least partially aligned spins. And how do you tell whether the spins are aligned or not? It's through the precessional effects and the gravitational waveforms. So at least this is not the sole motivation for caring about this, but at least for this talk, if we want to know where those binary black holes come from, the spin directions are a smoking gun signature of which channel, and we measure those spin directions through the precessional effects and the waveform. Did that? Okay, good question. Over there.
Yeah, so I have two questions. So the first one is of the 90 mergers that LIGO, Virgo, Kagra detected, most of them, like 88, have chi-effective very close to 0. So some people see this as evidence that spins should be very, very small. So do you have comments on this in light of your
yes, I mean, predicting the natal spin magnitudes. So remember, I had those three kind of sources of spin in my talk. There was fundamentally the cluster channel where the black holes come first, and then there's the isolated channel where binaries come first and the black holes come later. Obviously, if the black holes formed in individual systems, there were no tides to raise, no companion to raise tides on it before it collapsed to a black hole, and there was no companion to donate mass to get accreted onto it. And so for those systems, essentially only the natal channel would contribute. And if you believe that core envelope coupling is efficient. So essentially, even though, as we said, stars have, in principle, there's a large reservoir of angular momentum, which if just a small fraction of that got transferred to the black hole, it could be highly spinning. If the coupling is so strong that you lose 100% of that reservoir. So you could interpret that to be saying, essentially, if I was a big patron of the cluster channel, I could say, look, I mean, tides are tides. I mean, tides aren't going anywhere, but essentially it would favor the cluster channel and would favor strong core envelope coupling. That could be an interpretation of the small spins. Certainly as a population, there are events that do have significant spin, and certainly the population favors modest spins, 0.1 or whatever. They're certainly not all maximally spinning, but they're not all non-spinning either. You're right that chi-effective is, that's also more with the more details of chi-effective, I think is too much to, but you could also theoretically, if they were all in the plane, that would be a wildly precessing system that is you'd have to be, of course, really lucky for that to be true. But just because chi-effective is small doesn't prove that the precession is small. And if you actually look at their funny plots, those half moon plots that they show you, I much prefer our parameters to those half moon plots. You almost have a lot of allowed parameter space, in those fat wedges.
So I have a second question.
Or maybe you and then we'll follow up. Okay, go. Say yours.
Well, my second question was, when it comes to formation, having black holes and neutron stars is not that different. In the sense, your pathway is 1, 2, or yeah. So does this apply always black holes, or do you envision this framework also being applicable to neutron stars? And if yes, what would be the effect of, say, tidal distortion in the neutron stars where they merge?
That's a great question. So first of all, in terms of these kicks that I've been talking about, which are the kind of ingredients for the misalignment, the observational evidence for those comes from pulsars in our own galaxy. We see that the scale, if the pulsars, obviously stars predominantly form in the disk. If you have kicks that are generally misaligned with the galactic plane, that will kick you. If it's big enough, it would unbind you from the galaxy entirely. But otherwise, you'd have like a thick disk. And so by measuring the scale height of pulsars, you can kind of reconstruct what their typical kicks are. And they tend to be, something like 250 kilometers per second. In terms of the spins, people tend to think, you're right that they're quite compact, but the dimensionless spins of the pulsars are neutron stars in binaries are expected to be, I think, 0.05 or smaller, very small. And if you make if you make that prior, I mean, in terms of parameter spaces of trying to measure masses or even measure like nuclear equations of state, which people are very interested in, there's some degeneracies if you allow the neutron stars to have spins. I'm not an expert in neutron stars. All I can tell you is that I think that they're expected to have small spins. And what that's telling you about, I guess in terms of accretion, obviously if you accrete enough onto a neutron star, it's going to collapse into a black hole. So there may be a limited amount. If your neutron star is born, unlike a black hole, which kind of forms a black hole and then nothing's getting out of that event horizon, if you're a neutron star, you could potentially couple to your ejecta for far longer to transfer more angular momentum outwards, or you could even lose it once you're a black hole and you've got spin. The Kerr metric is a stationary solutions Einstein's equation, where highly spinning black hole neutron stars have magnetic fields and spin down, etc. You'd have a lot of time to spin down as you inspiral towards merger. So it's not clear. To some extent, the black holes could preserve more memory of their formation than the neutron star could, at least with regards to spin orientations. Was that maybe not a fully satisfying answer? Okay, go ahead.
Yeah, so kind of like following up on what Sam said, if we consider different theories of gravity, you have different modes of polarization.
Right.
So could it be that, and I don't know if there's any work that somebody has done like into detecting precession as a way of testing general.
I think there were some very recent papers looking at, you're absolutely right that in principle, if you had different kinds of polarization, that's going to lead you to, both the processing signals of different polarization are going to be very distinctive. And also you might get intrinsically different precession in a modified theory of gravity. I haven't worked in that area. People are just starting to think about, precession is kind of, people have been kind of qualitatively aware of this, but now it's finally, there are some evidence, it's a very hot topic. I think it's a work in progress. I think the best I can tell you is that qualitatively you're correct, but quantitatively I can't tell you more.
Gotcha. It seems like nutation is more physically interesting and more coupled to the spin. So has there been any constraint mutations in some of the LIGO signals?
I have not. There's been very little even attempts to constrain it, let alone there's no, I think to my knowledge, there is no, certainly no reliable detections of nutation. And even since it's like an order of magnitude harder than precession, which itself is hard to detect, there have been limited, focused study on that.
Okay.
But a very good question. I think, nutation is very exciting. Andrew, you have a question?
Yeah, sure. So mainly I wanted to, thank you for a great talk. I wanted to point out we got some representatives of our undergraduate astrodynamics class here, and this is a class that Caitlin developed, and Gabriele added a module on gravitational waves, and that I'm currently teaching. And so this really touches on a lot of the things that we do in that class.
Yeah, no, I do. I teach about precession nutation of tops in my undergraduate mechanics. Also, just one quick announcement before I forget. I'm at UT Dallas. We are currently doing a job search for a tenured or tenure track astrophysics faculty or gravitational physics faculty. So if any of you know talented postdocs that are looking for faculty positions, don't hesitate to, it's on the AAS job register, it's on our website. People are strongly encouraged to apply, and you can ask me if you want more information about that.
Are you also looking for postdocs?
I'm not currently looking for postdocs, but thanks.
But anyway, maybe quickly. So one of the things we do in the class is that in the standard conservative regime, where you have mass transfer, right, from a primary to a secondary, the direction of inspiral depends on whether the donor mass is the more or less massive one. And so you can remind me if is that standard regime, which of those regimes does that standard case where it's your massive star that's donating mass conservatively, does that correspond to one of your four cases?
So that's a good question. So first of all, in terms of conservatively, we've treated, I went through that, in the interest of time, I had kind of went through that kind of quickly. But one of the parameter on the x-axis here, this is the fraction of the donated material that's accreted all the way from 0, so that's no accretion. Conservative, where all of it were accreted, that would be 1, that would be all the way off the end here. I think people don't think it's that high. In terms of whether the donor is more or less massive, obviously the primary by definition is originally more massive. In our scenario A and scenario B, when you have wind mass loss, depends on metallicity. I mean, there's a lot of complications I didn't go into. Usually in the scenario A, where stable mass transfer was first, unless the winds were crazy strong or your mass ratio was so close to generally the donor there would have more mass. But in the in the scenario B, where the primary had already evolved, lost its whole envelope, and just clapped to a black hole, and that process is highly non-conservative, and so in that case, the secondary can actually be the heavier guy. And also you can get this mass ratio reversal too, where the initially heavier star forms a less massive black hole, and that leads to other complications, which I also, in the interest of time, didn't talk about. But my guess is that, crudely, in scenario A, it'd mostly be in the case where the donor is more massive, and in scenario B, well, I guess the donor is always. Generally, the donor will almost always be more massive. It's just that whether the donor will be the primary or the secondary is different in the two scenarios.
All right, let's, if people have more questions, they can come up and ask.